In the previous lecture, we talked about when X, our design matrix, is n by n of rank n, then fitting x beta to y through least squares is simply reorganizing y. This sort of reorganization works out particularly well when x is such that x transpose x is I. In other words, if xi transpose xj is 1 if I equals j and 0 otherwise, where xi and xj are columns of x. If this is the case, if xi transpose x equals I, then x transpose x is an identity matrix, and then our fitted values, our beta hat, is x transpose y, which is nothing other than the inner product of each column of x with y. So if x forms an orthonormal basis for Rn, then the fitted values are nothing other than the inner products of the columns of x with y. So our y hat is x transpose y, which, using this information, is nothing other than the sum of the columns of x times the inner product of xi and y. And you may recognize this formula, and we'll talk more about it. Notice, if you delete columns from x, let's say w happens to be the first p columns of x, then of course w transpose w equals I, and this is true if you pick any p columns of x, but I'm picking the first. Because of that, the best approximation is of the form, just following exactly the same logic from the previous few lines, the best approximation of y from this now rank p matrix, which is a subset of x, is the same formula where it's instead of the sum going up to n, the sum is just going up to p of the columns xi times the inner product of those columns xi and y. In other words, if your design matrix forms an orthonormal basis, then first of all, the fitted coefficients are nothing other than the inner product of the columns and y, and those fitted coefficients don't change if you drop columns of the X matrix from the fit. And we're going to talk a lot more about this, but I think it's an interesting result in mathematics, and you've probably seen this theorem before, this representation theorem, that the best approximation of y given an orthonormal basis is the sum of the vectors of those orthonormal bases times the inner product of the columns with the y's. You've probably, if you've taken some high-level mathematics, you've probably seen that formula before. Well, what are some important bases? Well, the Fourier basis, of course, is the most famous one, and that's where the columns of x are a couple of trigonometric series that are orthonormal. Principal component bases are another one, and wavelet bases are a famous one as well. So when you fit any of these bases, when you do it with a basis like this, especially for the Fourier case and the wavelet case, they don't call it fitting, they call it a transform. So when you do this fit and get the coefficients, it's not called least squares for the Fourier basis. It's called the Fourier transform because it's just transforming the y into another set of Fourier coefficients. Because of that, the best Fourier transform, if you were to delete some of the columns, would still be the same coefficients. And so that's this whole practice of filtering and getting rid of frequency components of a signal by deleting columns of the design matrix. So we'll go through that a lot in this class, but I just wanted to get started on it and thinking about bases and think about the least squares consequences when our design matrix is an orthonormal basis for Rn. The final point I would make is very little changes if instead of talking about Rn, we're talking about function spaces. So if you get used to the notation of inner products and things like that, then all of the same discussion carries over if our data and our bases all live in some sort of Hilbert space. Okay, so we'll go through a lot of examples in class, but in the recorded lecture part, I just wanted to get you oriented to some of the mathematics.